Okay, cool. My pleasure to be giving a talk here. Basically different levels of challenges in robotic assembly. And so we'll zoom in and out in the assembly process, and I'll talk about different challenges and our work to tackle these challenges and what's next. Okay. So when we look at assembly, it is still the least automated process in industry due to the contact-rich nature of it and also the high mix nature of it. So today I want to look at two levels of challenges of assembly. So when we zoom in, look at this very high contact-rich insertion phase of assembly. It's usually high precision and results in very complex contact dynamics. And when we zoom out, look at the whole assembly, it requires usually multiple parts, multiple steps, and oftentimes multiple skills required to do this assembly. It's a long horizon task. So I'll talk about these two levels. Let's focus on the zoom in part first. This is an earlier work where we asked this question. So when we're in this contact-rich stage of assembly, is force feedback enough to learn a policy? So intuitively, when we try to assemble something, when our hand is already in the vicinity, we can just close our eyes and do it by the touch feedback. So that's a question we asked. In this work, we propose this force-guided robot agnostic approach. So where we train a policy in simulation was actually without a robot, was just an end effector and the parts. Somehow. I'll try to. How about now?
You just put it right here.
Oh, here?
Yeah.
How's it now?
Yeah.
Okay, cool. And we can deploy this train policy on different robots. Here's a distributed RL training framework we built upon Apex DDPG, which I will not go into details. Here it shows, this is the same policy that's deployed on different robots, different tasks, with noise added, and also with different target pose. So this is all in simulation. In this work, in collaboration with the architecture group at ETH Zurich, we apply this approach to timber joints assembly. So the vision is to build this freestanding architecture, like the structure, with tight-fitting timber joints. And you make robots learn how to put this together. So we collect a few human demonstrations of putting together these timber joints in simulation, and then we train it in simulation with RL approach and deploy the trained policy on the real robot. We'll see in the next frame. So here, this is real experiments at the ETH Zurich, where we roll out the same policy on the wood joints with different, very small at the time, small linear offset and angular offset for the joints, as well as different joint angles. It was trained on the 90-degree joint angle. We tested on 75 and then 60 degrees in the joint angle. It can still work, but it won't work beyond that. We can also train different policies for different joint shapes, for example, like H-shaped double lap joint. So far, we've looked at the situations where there's no uncertainty in the grass pose. we assume the parts are already stably grasped in the gripper, and there's no uncertainty in that. So in this work, we look at what if there's uncertainty in the grasp pose, or when there is slippage during grasp. And so we mounted a digit tactile sensor on one finger of the Panda robot. There's a wrist mount camera, and then we get force feedback from the Panda robot. So here we use a tactile feedback to guide the grasp alignment policy, and then use vision to guide the insertion policy. The force torque feedback is used to find safe self-supervised data collection. On the left, it shows the self-supervised data collection process for tactile images and to learn the tactile policy. And then on the right, it shows the data collection process for the image-guided insertion policy. Here it shows some results for tactile-based grasp pose estimation. So we can achieve pretty small errors, but still not perfect. Some examples of the insertion from the system of USB connector. We achieved 100% success rate while using behavior cloning or some online RL algorithm. They did not work really well because of a lot of the slippage happening in the grasp. And so far, so the work I've talked so far hasn't really looked at generalizability. So this work, we propose an approach to see, can we train on a single task in simulation and have that generalized to very different assemblies, ranging from electronic connectors to some real industrial parts to 3D printed tight peg and holes. And this work came from this observation about the sim to real gap during the assembly process. So one important observation is that even with the same insertion policy, when we apply it to different domains, say sim to real, sim and real, the contact force is very different. And we believe that's the main cause for the policies not working in a different domain for this contact-rich insertion tasks. So the approach we took is we did on offline training in simulation. So we use an off-the-shelf RL agent to generate data, the sim data. We train two separate neural networks. One is a force planner that plans both robot motion and contact force. And the gain tuner predicts the corresponding compliance gains. And then in online phase, during execution in the real world, the force planner takes trajectories from running in the real world and output both the robot motion and desired contact force. And then the gain tuner tracks the desired contact force with the appropriate compliance gains. So this way we could achieve pretty good sim to real transfer, as well as transferring to different insertion tasks. So here shows some examples. So on the top row, you see 3D printed peg and holes, but they have really tight clearance. So 20 microns at the smallest one. And fun fact, you can see they're so tight, the pegs fall off out of the gripper after insertion. And then on the bottom left, if it's, there we go, shows the skateboard truck parts. The clearance is negative because the rubber bushing will have to insert into. They're deformable. You have to deform the rubber bushing. And then we also tested on some electronic connectors just to show very different geometries can still work. So some takeaways for the contact-rich stage. So we think for this very contact-rich zoomed-in stage, force feedback is important, and we think it's more important than vision. And tactile sensing can help when you have uncertain grasp pose or slippage in hand. But so far, we have only trained that in real. But after Yash's talk and he and his colleagues' work, maybe we'll have a good tactile simulation to do this training in sim. And then we think the main sim to real gap lies in contact force in the stage of assembly, and compliance is key. Compliance in the robot motion. Okay, so let's zoom out to look at the sort of the whole assembly where there are multiple parts, probably multiple skills required. It's very long horizon, and how do we solve these problems? So this work was led by Yongsheng from MIT. It's our collaboration project. This one looks at the assembly sequence planning when you have multiple parts in an assembly. How do we plan the sequence while considering physical feasibility? This is a nice video Yongsheng made with captions, so we can just watch it, and I can pause talking for a bit.
That's the word. Yeah.
You should.
So, yeah, we just proposed an assembly sequence planner that can plan basically the whole assembly process from the beginning, which is every part individually, and finally the end assembly. And we think about the sequence, the paths, the grasp, and also the motion during. And this is our workout, just demonstrating we can use the same pipeline that generate this assembly whole assembly process for many different kind of assemblies.
Great. Next, let's look at, so even for the same part, there could be multiple steps in an assembly. For example, you need to reorient your part. maybe with some kind of fixture. So this is the FMB data set, where they have different shapes of pegs, and sometimes reorientation is required. So multiple steps. So when we look at such long horizon tasks, there are some challenges, right? So like, there is still the high precision contact rich part that we need to figure out for insertion. But then the long horizon task, we can't just sequence the different steps together because the errors will compound and it will not work. So some existing methods, right? So there's end-to-end imitation learning, but that requires a large amount of data, large amount of human demonstrations, like many talks have mentioned. There's also reinforcement learning. We showed reinforcement learning is very effective for the contact-rich part, but when dealing with long horizon tasks, I think RL is not the way to go. It struggles. And there are also the task and motion planning approach, but that requires a lot of hand design transition functions between your different primitives, and is computation intensive. So in this work, we propose an hierarchical hybrid learning approach where, can you see my mouse? Yep. So where we have a low-level skill library or primitive library, where we have pre-trained RL policies for insertions, basic skills that require contact-rich, high precision, this kind of requirement. And we also have motion planned policies or skills, where in free space, we can just connect different skills together with motion planning. And on the high level, we have an imitation learned policy, which takes also pose estimation for where the object, they find out where the objects are. Also for the RL policy training, we use for stork feedback. So let's look at some of the skills, the low-level skills we have, and this is in i6M and i6 Lab for RL training. There's, you grasp the parts, there's move, there's place, and insert. Insert is trained with RL. On the high level, we use a diffusion transformer. Here's the architecture, and that outputs basically it predicts the primitive candidates for the current task. And what's cool about it is the human demonstration is very easy for this high-level policy, because we just select the primitive indices during the demonstration, and the underlying policy is already pre-trained. And so data collected without teleoperation. And we have some example primitives or skills here shown on the bottom. So I show some examples. This is trained on a hexagon project part. And then so this is a scene object, and based on different orientation positions, it will choose to reorient it on the fixture or not. And then we can use the same policy to transfer to different objects, they're unseen objects, onto that board. So some objects are more difficult. For example, the square circle, there are some failures there. Here shows some comparison with baselines. So we show success rate as well as success rate per weighted by path length. And we consider human oracle has the higher bound on the performance, and we perform better than other hierarchical approaches, and the end-to-end approaches just completely fail. And the right-hand side shows the data of the approach. Because of a hierarchical framework, we can just have 10 demonstrations and it can achieve high success rate. Here we show basically the system running continuously until all the pieces are inserted on the board. It can recover from failures. For example, the insertion failed here, but it can continue to do the grasping and then insert. So the object pose here is obtained from pose estimation running in real time. All right. So some takeaways from my talk. One, well, we talked about for the contact-rich part, these are the takeaways. And then for long horizon, sort of the whole assembly, I think the hierarchical approach is the way to go. It's a lot more efficient. And with the low-level skills, you can pre-train it, especially for the contact-rich part of skills, do the RL training. And on the high-level planning and composition of skills, can use imitation learning where you don't need as much human demonstration, or with a large language model. In the end, I just show a quick video. This is a project we did at Autodesk a year ago, where we want to autonomously assemble this skateboard truck. So here's the CAD model you see, and then we have the whole work cell in simulation. 3 robot arms. One is just holding a camera, which can move. And so here, the part sequencing and the long horizon sequencing is not autonomous, not learned. In this project, it was still manually defined. And as well as some of the grasp locations are manually defined. So we have a tool changing station where, because different part or different step requires different tools. So we'll change to a different tool station, regrasp, and then insert a part. So a natural extension of the last project would be to extend the long horizon to including the tool changing, etc., for this very complex, more complex assembly task. Due to time limit, well, in the end, come to intern with us. Thank you, and I'm happy to take questions.